Hey everyone, welcome back to the channel and welcome to the first lesson of our astronomy unit. So this is where we really kick things off for our science class. No more intro stuff, at least for the time being, not until I have some fresh updates to give you. So in this lesson we're going to be talking about scientific notation and some of the units of measurement that we use in astronomy. And you're going to see why we have to use some different ones in astronomy. But first things first, let's talk about what scientific notation actually is. So this is going to be a bit of a crash course on how exponents work. So this is a little bit of math, just so that you guys can get a feel for, what this is and why it's useful. So basically what scientific notation does is it gives us a really compact way to write really big numbers or really small numbers. So what I mean by that is, so for example, if I had, well, let's just use the examples on the screen so that I don't have to write anything in my handwriting. But we'll look at several examples here. So basically what happens is we use the rules of exponents to write down really big numbers in a very small, compact way. So this is basically just a space saver, and it's a faster way to write down big numbers. And I could say big numbers in a couple of different ways. I could mean something like this, where the product of 4 times 4 times 4 isn't actually a very big number, right? It's 4 times 4 is 16, times another 4 is 64. That's not a huge number. I could write that down in any size space I wanted to. It takes almost no time to write that to write that down. So it's not really a space saver that way. But if I wanted to write down 4 times 4 times 4, that takes up a bit more space and a bit more time. So it's a bit of a convenient notation to write it this way. So here's how exponents work, basically. You guys should remember this, but just, it's the beginning of the school year, get those brain juices flowing again. Basically, we've got the same number multiplied by itself some number of times. In this case, with 4 times 4 times 4, we've got 4 multiplied by itself again. So we've got a total of 3 fours, 3 instances of the number 4 being multiplied together here. So when we write that down with an exponent, the big number here is the number that's being multiplied together. So in this case, it's the 3 fours. So since we're multiplying 4 by itself a bunch of times, we write a big 4 here. And then the little number up there, which is actually the exponent, that number is telling us how many times we see this bigger number in our multiplication. So if we've got the number 4 being multiplied a few times, so we have a big 4 here, and if it's being multiplied together 3 times, then we put a little 3 in the exponent. And you can see that we've got a couple of similar examples here with 12 being multiplied by itself several times, and if we count that out, it's 1, 2, 3, 4, 5, 6, 7. So we've got 12 being multiplied by itself 7 times. So when we condense that down to write it as a power with a base being the big number and an exponent being the small number, the whole thing is called a power. So when we write it as a power, we've got a big 12 because that's the number that's being multiplied together, and then we've got a little 7 in the exponent because we're multiplying 12 by itself 7 times. So that's how the numbers work. And I haven't worked out the math. If you guys are interested, you can do this as a little exercise of figuring out what 12 times 12 times 12 times 12 times 12 times, all the way to 12 to the power of 7. If you want to figure out what that actually is, go for it. It's probably a very large number because 12 times 12 by itself is 144. So you already know that you've gone from a number in the tens to a number in the hundreds when you multiply it by 12 once. So you're going to hit the thousands and the 10,000s and bigger numbers as you go along. So this ends up being a really condensed way to write out what would otherwise be a very large number. And even just this multiplication itself, without figuring out what it's equal to, this is a really long thing to write, right? We got to write the number 12 7 times, and we got to put the little multiplication sign 6 times in between. It's really long. It's easier to just write down the 12 with a little 7 up there, and this expression here is what that actually means. So This is how we use exponents. And there's another example down here at the bottom. It's kind of the same idea with, we've got the number 2 being multiplied by itself 10 times. So since the 2 is what's being multiplied, that's the big number here, the larger font number here, called the base, and then the exponent, the little number at the top, is the 10, because we've got 10 instances of the number 2 being multiplied together here. So that's how exponents work. This is just sort of part 1 of 2 on how scientific notation actually works, because scientific notation makes special use of the number 10 and what happens when we multiply 10 by itself a bunch of times. So in scientific notation, you won't necessarily see other numbers like this 12 to the power 7. That's just writing it as a power or with an exponent, but that's not necessarily scientific notation. Scientific notation makes specific use of the special properties of the number 10 when we multiply 10 by itself a bunch of times. So let's see how that works. So here's the neat thing with the number 10. If we start, this is the same thing as what we saw on the previous slide, right? We've got 10 multiplied by itself a bunch of times. So we write it down as 10 as the big number because that's the number being multiplied. And then up here we've got a little number that tells us how many times that big number shows up. So the big number here is 10, and we've got 10, 10, 10, 10, 10, 10. We've got 6 of those over here. So we write 10 to the power of 6, or 10 to the exponent 6. And then it's the same idea here, but this time we've got 9 instances of the number 10. So we write it as 10 to the 9. And then down here we've got the same thing, but it's 10 to the 12. We've got 12 instances of the number 10. I really hope I haven't miscounted the number of times that I've put the 10s in here. There's a lot going on this slide with all the numbers and all the multiplication that it starts to kind of look the same. But the idea is there's supposed to be 6 up here, there's supposed to be 9 in the middle, and there's supposed to be 12 at the bottom. And so we have these condensed ways of writing down these numbers, but here's the neat thing with what happens when we try to multiply 10 by itself a bunch of times. So let's start small. Let's start with just this top example, and we'll go step by step. So first things first is 10 times 10. Well, 10 times 10 is 100, right? Easy enough. And if we just sort of keep in mind what it means to multiply two numbers together, then we can keep going and discover the pattern. So if we have 10 times 10 is 100, if we multiply that by 10, now what multiplication is really saying is that you've got some number of groups of some other number. So in this case, we've got what we're trying to do from this first step to the second step is we already got in the first step that 10 times 10 is 100, and now we're trying to multiply that by 10 again. So you can think of this either way. You can think of this as 100 groups of 10 or 10 groups of 100, but however you go about it, you'll come out with the answer that 100 times 10 is 1,000. And if we repeat that process, multiplying it by 10 again, then we'll get that 1,000 times 10, well, that's 10 groups of 1,000, which is 10,000, which looks like this. So I'm not going to keep going just because I don't want to fill up the space, but I am going to point out the pattern. When we started with just a 10, we had a 1 followed by a 0, right? Then we multiplied it by 10. We got 100, so that's a 1 right here, followed by 2 zeros, right? Then we multiplied it by 10 again, and that's 1,000, which is a 1 right there, followed by 3 zeros. And this is the pattern of when we multiply numbers by 10, we just end up tacking on a 0 to whatever number we started with. So if we multiply by 10 again, that's with this one here, then we get a 4th 0. That's 10,000. That's as far as we went over here. But if we just continue it on using this pattern, if we multiply it by 10 again, we just add another 0. And if we multiply by 10 again, we just add another 0. right? And this number here is 1 million. Now, whether or not we give it a special name, like a million or not, that's not the most important thing. The thing I want to point out is that there's a special thing you might notice here, is that the little number in the exponent, that's 6 right there, is the same number as how many zeros there are in the actual answer, the actual product. If you went through and multiplied 10 times 10 times 10 times 10 times 10 times 10, you'd end up with a number that's the number 1 followed by 6 zeros. And when we try to condense that down into scientific notation, which is basically, for now, it's just condensing it down to writing it as 10 with some exponent, that exponent is a 6, and the number of zeros is 6. Neat. If we continue that with this second example, we'll find that that pattern holds. That pattern ends up being exactly the same. So if we do it for the second example, we start with a 1. Well, we can say we start with a 10, right? And then we multiply that by 10. So we add a 0 because we go from 10 to 100, right? 10 times 10 is 100. And then we multiply that by 10 again. So we get 1,000. And then we multiply that by 10 again, and we have 10,000. And we multiply that by 10 again, and we have 100,000. We multiply by 10 again, we have a million, 6 zeros, right? Multiply by 10 again, we add another 0, that's 10 million. We've got 7 zeros now. Multiply by 10 again. Now we've got, that's what, 100 million. That's 8 zeros. And multiply by 10 again, add a 0, and now we've got 1 billion. That's a 1 followed by 9 zeros. And I've just put the commas here. I don't like to write large numbers with commas. I prefer to write them with spaces, but just because that's sort of what I was taught in school here in Canada. But because I couldn't put those spaces in because I was writing one number at a time, I'm using the commas now, which might make it a little bit easier to see that this is the number 1 billion. But anyway, so what's interesting here is that if we count up the number of zeros here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, right? We've got 3 groups of 3 zeros. So we've got 9 zeros here, and the exponent is a 9. So this pattern holds for any time that we're multiplying 10 by itself. We could multiply 10 by itself 100 times, and our little exponent would be 100. And actually that number's got a special name. It's called a googol, not spelled the same as Google, the search engine. But anyway, this pattern works when we're multiplying 10 by itself however many times we want. So if we want to multiply 10 by itself 25 times, then we could condense that down and write it as 10 with a little 25. For example, right, if we had a 1 followed by 25 zeros, or 10 times 10 times 10 times 10, 25 times, then we could write that in this shorthand. So you can see that for a number like this, a number like a billion, it's several digits to write that out, right? It's a long number. When you're dealing with numbers in the billions, you're going to have at least 10 digits. They might not all be ones and zeros like we've got here. You know, if you're talking about like 4,538,000,000 and so on, you throw in other digits, the digits can be whatever, but you're going to have a 10-digit number. So if you want to condense that down into a simpler form, and it's easier when it ends in a bunch of zeros, but anyway, when you want to condense a large number like that down to a smaller form, then we can use these exponents to really condense down the way that we write it. And so the same thing follows for this last one. I'm not going to take you through the process of this last one because it's the same idea as the two before that. But what we can see, I'll just give you the answer here, is that for each of these 3 cases, we end up with the answer, if we actually compute the answer by going through the multiplication, we get these fairly large numbers, right? We start out with a million, which maybe isn't an enormous number, and then we've got a billion, which is a very big number, and then we've got a trillion, which is a number that, honestly, even with a million, it's difficult for our brains to picture a million of anything. and it gets harder to picture a billion of anything, and I don't think I can properly grasp the size of a trillion of anything. But anyway, the idea is we've got this really large number, a trillion of anything. We could say, a trillion, I don't know, atoms in some object, and you want to write down how many atoms there are. You could write down this number over and over if you wanted to, or you could write it down as 10 to the 12. And that's how we sort of read it out. We can say 10 to the 12, or 10 to the power of 12, or 10 to the exponent 12. All of those things you'll hear people say it different ways. As long as your idea is conveyed properly, then it doesn't matter which one you choose. I'm so accustomed to using exponents that I sort of use that shorthand form that's like 10 to the 12, and I don't bother with saying power and exponent and all of that. But yeah, anyway. So this is what we can begin to see the usefulness of scientific notation with. But so far we haven't seen any sort of practical usage for this notation. So let's explore that. So if we wanted to talk about, let's start thinking about things in space. So we can think about, maybe we've spotted an asteroid somewhere in the asteroid belt, and we want to talk about how big it is. And you take some measurements, and you find that it's got a diameter of 1 million meters. Now, that's not actually very large for an astronomical object, but we could write it in various ways, right? We could write it as 1 million meters, or we could recall by our usage of the metric system, which you guys either have seen or will see shortly in your math class, that we could write 1 million meters as 1,000 kilometers, because 1 kilometer is 1,000 meters. So we could say it's got a diameter of 1,000 kilometers. That's fine. Or we could start to use this exponent notation. We can look at, okay, well, when we write it out as 1 million meters, we've got a 1 followed by 1, 2, 3, 4, 5, 6 zeros. So I could write it as 10 to the 6 meters. Fantastic. And I could do the same thing with kilometers. I could start with this 1,000 kilometers, and I could say, okay, well, 1,000 is not a very large number, but just for my exponent practice, it's a 1 followed by 1, 2, 3 zeros. So I can write that down here as 10 to the 3 kilometers. So those are all exactly the same size. These four numbers are all talking about something that's exactly the same size. If you have an object that's 1 million meters across, or 1,000 kilometers, or 10 to the 6 meters, or 10 to the 3 kilometers, those are all identical sizes. And for these smaller numbers, like 1,000 kilometers, it doesn't take that long to write down the number 1,000. It's not that confusing to look at. If you just look at this right here, it's not the most confusing thing in the world. It's easy to write it down. It doesn't take long to write it down. You don't lose count of the numbers. So it's maybe not the most useful for numbers this small. I say small even though we're talking about thousands and going into millions. But for larger numbers, like if we're talking about the mass of the Earth, how much stuff goes into making up the Earth, or if you want to think of it as how much the Earth weighs, that's not entirely correct, but mass and weight are different. But for now, we can ignore that difference. We'll just say how heavy the Earth is, and we wanted to use a number to describe that. We would get that this is the number. This is how much matter is contained within the Earth, or for simplicity's sake, how much the Earth weighs. And that's a very big number. But fortunately, we can make use of scientific notation to really condense it down. So here's how we condense things down. It's very beneficial, and for the most part, you'll only ever see the first few digits will not be zeros, and then people don't care about what the rest of the digits are. So there'll just be a bunch of zeros after that. So the way we write things down in scientific notation can be a little bit confusing. So the proper way to do it would be you take the first digit only. So in this case, that's a 5, right? And then you put a decimal point. So we've got this dot, right? So we've got 5.5. And then we put the next few digits. So that's what we see down here as well, right? We've got this 5.972, right? So even though those numbers after the 5 are not all zeros, even though these digits here are not all zeros, we put the decimal point right after the 5. So we've got 5 point, and then we write in those other digits. We've got 972, just like what we have here. And then the way we write it out for the rest of it, here's just a general rule. You could explore this, or we can talk about it in more detail sometime if you have questions. But for now, I'm just going to give you sort of the mechanism of how to write such a number in scientific notation. So what you do is you write the first digit, put a decimal point, then you can write the next few digits, especially if they're non-zero, maybe write in the next few digits, like what we see here. So we've got 5.972. And now for that exponent, here's what we do. Here, now I'm going to add in a little decimal point right there. Okay, that's a fairly large decimal point, but I want it to be obvious. So I've added in this decimal point down here in this number, in this very large number. And so what we've got is the 5.972. And now for the number in the exponent, what I need to do is I need to count how many digits show up after the decimal point. Whether there's zeros or not does not matter. You could write in as many as you want or as few as you want. The number in the exponent does not care about about what the digits here are or how many you've chosen to write down. All it cares about is how many digits appear after the decimal point. So if we count those out, we get 1, 2, 3. And now I've separated all the numbers by spaces, so I'm going to count them in groups of 3. So we've got 1, 2, 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we've got 24 digits after this decimal point that we added in. So the way that we write this down is we write in the first digit, the decimal point, the first few digits after that, times 10 to the exponent of what we just counted, the number of digits after the decimal point, which is 24. And the idea behind this is, if you remember, hopefully you remember, but no worries if you don't, we will explore this again in our math class or talk about it sometime. But basically the idea is, if you have a number like, let's say, 2.6, and you multiply it by 10, what you're effectively doing is you're taking this decimal point and you're chucking it over to the right by one spot. And if you multiply it by 100, you're chucking it over another spot to the right. And if there's no digit there, then you write in a 0. Things like that. So I'll write that a little bit more cleanly. So we started with 2.6, and if we multiply that by 10, then it becomes 26. Right? So what we've effectively done is we've taken this decimal point and we've chucked it over one spot to the right. So that's effectively what we are doing down here. What we've done is we've introduced a decimal point at the beginning, but what we've really done is the decimal point was actually right here after the number in the ones place. And what I've done is I've brought it 24 spots over to the left. Right, the decimal point was actually over here. It's 5972 blah 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 0.00000. So I'm taking the decimal point, the invisible decimal point that sits here, and I've brought it 24 spots to the left over there. But I can't just move the decimal point over. I have to make up for that. So if I've moved the decimal point 24 spots to the left, I have to multiply it by a number that can take the decimal point 24 spots over to the right. And that number is 10 to the 24, or a 1 followed by 24 zeros. So hopefully that's not super duper confusing. This is just sort of an idea of how scientific notation is useful, but I'm not going to be asking you to convert numbers into scientific notation and things like that. I'm just trying to get you to see what this kind of a number here actually means so that you can visualize that this is the number that it stands for if we get rid of that decimal right there. So this number in here, this 5.972 times 10 to the 24th power kilograms is equal to this very large number over here. And that's what that number is actually trying to represent, but we try to write it down in this more condensed form. This is a shorter, quicker, easier way to write it down than having to go through and write down all the digits. And maybe you'll insist, well, you know, if I didn't have to learn scientific notation, then it's easier to just write down all the digits. But, well, sure, but what if you have to write down 150 digits or 300 digits? And it's not the answer to your question, it's the start of your question. Unlike a homework assignment, you're dealing with a number that's 300 digits long. You don't have the time or the space on your page to write down such a large number. So at some point, whether you think 24 digits is too short for you to bother learning about scientific notation or not, at some point it would become very, very difficult to write down large numbers, actually writing them out from the first digit to the last digit. Instead of that, we use this kind of notation. And what we can do if we want to simplify our lives a little bit further is, looking at this very last line here, I've changed the 5.972 into a 6, because 5.9, if you're looking at a number line, if we're looking at a number line and we've got, let's say 4 over here and 5 over here and 6 over here, 5.97 is like right there, right there. So that's basically 6. So I'm going to round that off and I'm going to call it 6 times 10 to the 24th kilograms. Just so that I can sort of have a rough idea in my head that the mass of Earth is a 6 followed by 24 zeros. Now I'm not going to write all those out because, well, we've got better things to do, but that's the way you can sort of think about it. Now let's come to why scientific notation is actually useful in astronomy. Now, this is one of those questions where I'm trying to answer, when will I ever need this? So basically, if any of you are interested in astronomy or interested in reading about it, you don't have to like want to study this or do this for the rest of your life, but if you are interested in reading up on things about space, and then you come across these big numbers that are describing things that we see in space, it could be the size of an object, it could be the mass of an object or how heavy it is, it could be how far away something is, it could be how old something is. We end up coming across a lot of really, really big numbers in space. And the reason for that is basically just that the universe is really big, so it's easy for things to be very, very far away. And stuff in the universe is really big, so it's really easy for them to get very, very large and very, very heavy in terms of the units that we use down here on Earth, right? Like, to give you an example of what I mean, it's a lot easier to talk about, well, the height of a person in meters or feet or inches than it is to talk about the height of a person in millimeters. Just because the millimeter is so unbelievably small, it's just not the best use of a measurement device, right? I would rather take a ruler, like your standard 30 centimeter ruler, or something of a roughly equal size. I'd take like a book or something, or a notebook, and I'd measure my height and say I'm this many notebooks tall. But if I had to say I'm this many grains of rice tall, that's really, really difficult to measure properly. I would rather stack a bunch of, you know, your notebooks that you guys bring to school. I would rather take a bunch of those notebooks and stack them on top of one another and say, okay, I'm this many notebooks tall, versus having to stack rice grains on top of one another. So basically, the units that we use here on Earth, even though they seem really big to us, like kilometers and miles and things like that, when we start talking about things in space, a kilometer is really small, and a mile is really small, and a meter is unbelievably tiny, and feet and inches are useless when we're trying to talk about things in space. They're just too small. It's like trying to measure the height of the Eiffel Tower in I don't know, pencil sharpeners or something. Like it's the most inefficient way that you could possibly think about trying to measure something of that size. And so what happens is we have all these units that we use in our daily lives. We use meters, we use kilometers, or miles and feet and inches, whatever you prefer. And we use pounds and we use kilograms and we use seconds and hours and days and weeks and you know, we use a whole bunch of numbers and units in our daily lives, but they're so small when it comes to talking about things in space. So I'm going to show you, I think it's on the next slide. Um, I'm going to show you some numbers that we use to characterize things in space, to describe things in space. And you'll see that the numbers are just too big for us to really make sense of with our puny little units down here on Earth. And so they end up being really large numbers. So let's take a look. I think it's on the next slide. Okay. Well, this is what I was just saying a moment ago about the kinds of things that we use in daily life. The units of measurement that we use in daily life are things like meters and kilometers for distances, or kilograms or pounds for masses, pounds being the imperial version of the kilogram. And then for times, we talk about things that happen in seconds or minutes or hours, days, and you could throw in weeks and months, but I've just, you know, I've given a few that we use, right? You could add in centuries and you could add in months and weeks and stuff, but these are some of the units that we use in daily life. The problem is all of these are too small to talk about things in space. So let's take a look at that. So here are some examples of numbers that we might want to know about things in space. So we might want to know the mass of the Earth, which you can think of as um, how much material goes into the Earth, or slightly less accurately, you could think of it as how heavy the Earth is, and you could think of how heavy the Sun is. And you can think of the size, like the diameter of the Milky Way galaxy. So if we've got a galaxy that's, you know, you've got like the center of the galaxy here, and then you've got these big spiral arms that go out like that, and you want to know the size of the galaxy, let's just say from here to here, and we can ignore the outer part of the spiral arm there and the outer part over there. But even this distance, what kind of units am I supposed to use to measure that? Because it's like trying to measure the height of the Eiffel Tower in pencil sharpeners. It's just not useful, right? It's like trying to measure the distance between New York and London in iPhones. Like the units that we know of are so small that you could measure the distance from New York to London in iPhones, but it's going to be a lot of iPhones, right? It might be millions of iPhones. I haven't done the math. I'm just throwing numbers out there. It could be millions of iPhones. It might be thousands of iPhones, but well, it's probably a lot bigger than thousands of iPhones. But anyway, um, we can use the units that we already know about. We can use meters and kilometers. The problem is that we just need a lot of them to describe things of this size in the universe. If we're talking about something the size of a planet or a star or a galaxy, uh, we end up needing bigger and bigger numbers to describe how heavy they are and how big they are. And if it's not something that's in our solar system, we need big numbers to describe how far away they are, or like how far away the next galaxy over is from us, or the galaxy after that, or the galaxy after that. And so what happens is we have really heavy things in space, really large things with a lot of material in them. So we have really big numbers for their masses. And they get really big, really large physically in size. So we get really big numbers for when we're trying to describe like the diameters of these things. And they can be really far away, so we might need big numbers to describe their distances. And the universe is so old and things play out so slowly that we need really large numbers to talk about time as well. So I'll give you some of these numbers. I'll give you the measurements of these different numbers, the mass of the Earth, the mass of the Sun, the size of our galaxy, the distance to the next galaxy over, bonus points for anyone who can tell me what the next galaxy over is, and for the age of the universe as it's currently understood by scientific tools. Here are the numbers. As you can see, they are immense numbers. We're not going to bother going through and trying to say all of those like in terms of like octillions of kilograms or anything like that. I'm just gonna, you can just look at these numbers and you can see that they're very large and really difficult to read, right? The mass of the sun, it's really hard to figure out what that number is actually called. You'd end up probably just saying 198900000 and going through until you get to the end of the list and hoping that you don't miss any of the zeros or double count any of the zeros. Right? These numbers are difficult to use, difficult to say, difficult to write down, and they take a lot of time and space to write down. So here's where scientific notation is useful. We can condense these down using the same techniques as we did before by writing them using the exponent rules that we saw before. So for example, we already talked about the mass of the Earth, but for the mass of the Sun, we could introduce a decimal point right there, and then we could write it out as 1.989 times 10, and then we need to figure out what the exponent on that is. And the exponent on that, if you remember, is however many digits appear after the decimal point in the original number once we introduce that new decimal point. So if we go through and we count them, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 21, 24, 27, 30. So we've got 30 digits after the decimal point. So our exponent right here is a 30 kilograms. And that is the mass of the sun. It's exactly the same number as the really long number that you can see right here, but of course getting rid of that decimal point because that decimal point shouldn't actually be there. But yeah, so when we write it in scientific notation, we introduce that decimal point after the first digit, and then we can write it this way in a much shorter, much more condensed form. The only thing that really takes time is counting out how many digits there are after the decimal point. And for some numbers, depending on how useful the number is in whatever you're studying or whatever you're trying to do, you'll probably just end up memorizing that number. So for the mass of the sun, I just memorized that it's 1.989 times 10 to the 30 kilograms, and I never have to write out the long form, and I never have to count out all those digits. I just memorize this one here, and I just write that down whenever I need it, and then I use exponent rules and things like that to work with that number when I need to. But that idea applies for all of these. And I'll just go through this one of the size of the Milky Way as another example to show you the scientific notation thing, but I'm not going to bother going through the last two there. Those are for you guys to practice. So if we want to write this out, the size of the Milky Way, in scientific notation, well, our first step is introducing a decimal point. So then I can write down a 1 point. And I could say 1.0, right? I could say 1.0 or 1.00 or however many digits I want to write. But that's all the same thing as 1, right? 1 is the same thing as 1.0, and it's the same thing as 1.00, and the same thing as 1.000. So I don't actually need to write anything after the 1. I don't even have to write in that decimal point right here. So I can just leave it as a 1. And then I can write times 10. And now we need to figure out what the exponent on the 10 is going to be. We need to figure out what that exponent is. So I'm still leaving that little decimal point that we put into the actual number so that we can count the number of digits after that decimal point. And if we go through and count it, we get 3, 6, 9, 12, 15, 18. So we've got 18 digits after this little imaginary decimal point that we've introduced here. So we get an 18 as our exponent after the 10, right, as our exponent on the 10. But we can make this even easier. I don't have to write this as 1 times 10 to the 18. I don't have to write this as 1 times 10 to the 18 because 1 multiplied by anything is just going to give you back whatever that number is, right? Anything times 1 is just the same thing that you started with. Multiplying by 1 doesn't change anything. So I actually don't even need to write in this much. I could just say that the size of the Milky Way galaxy, I don't know why I wrote kilograms, sorry about that. That should be kilometers. Sorry about that. But yeah, anyway, the size of the Milky Way I could just write as this. I don't need to write a 1 times that because multiplying by 1 doesn't change anything. So we end up with this as the condensed version of the size of the Milky Way. And so I wanted to go through that example to show you what happens if the only digit out in front is a 1 and you've got no other digits like the 5972 or the 1989 over here. If it's just a 1 followed by a bunch of zeros, you don't need to put anything in front of your 10 to the power of whatever. So that's how that works. For the last two, I'll show you the answers, either on the next slide or in a few slides' time. I kind of forget how I set this up. But I'll show you the answers. I'm just not taking you through it step by step. If you have questions about it, if you're not able to figure out how I got from the number that you can see on the screen right now to the condensed scientific notation version of it, then let me know and we can talk about it. And I can make another video about it, or we can meet up over a Zoom call or something to chat about it, and I can answer your questions there. But yeah, so what we can see here is the immensely large numbers that we end up seeing in things in space just because our units are too small to describe them. It's like trying to measure the height of the Eiffel Tower in pencil sharpeners. You're just going to need a lot of pencil sharpeners to actually measure that. Okay, perfect. So I did put the scientific notation form right on the next slide. So you can see now that this is how we could write those numbers down in a more condensed way. And for the size of the Milky Way, for the time being, I left in this 1 times in front. But now you can hopefully see that we don't actually need that. But anyway, these are the numbers that we end up using. These are the numbers that we end up finding with the units that we're using. But there's the thing. You could use scientific notation to write really big numbers in a really compact way like this, or you could invent larger units, right? It would be like if we only had the meter, but we hadn't invented the kilometer yet, and then somebody asked somebody else, hey, can you measure the distance from New York to London? They're going to either give a really big number in a small unit of measurement, like a few million meters, or they'll give you a smaller number in a bigger unit of measurement, right? Hopefully you can see the logic in how that works. I could say the Eiffel Tower is, I don't know, 2 million pencil sharpeners tall, or the Eiffel Tower is, I don't know, like 3 pyramids of Giza tall. I don't know the heights of the two buildings, so please don't hate me for getting that wrong. But hopefully you can see what I'm trying to get at, right? I could say the Eiffel Tower is 2 million pencil sharpeners tall because pencil sharpeners are really, really small and the Eiffel Tower is, well, not so small. Or I could say it's like 3 pyramids of Giza tall because the Great Pyramid of Giza is very large. It's a much larger unit that if I stacked that enormous thing on top of itself a few times, I would only need a couple of them to reach the height of the really big buildings that we see around us today, right? I was going to give a stupid example of saying that the Eiffel Tower is 1 Eiffel Tower tall, but that's not really helpful. But hopefully you can see what I mean with this Great Pyramid business, that either you'll end up getting a really big number with a very small unit, or you can get a smaller number with a bigger unit of measurement. And so that's where these new units come into play. So for lengths and distances, we already talked about how in our daily lives we tend to use meters and kilometers. Problem is, those are too small for making measurements in space. Not all the time. If we're talking about planets and how big they are and how close their moons are to them and stuff, meters and kilometers work just fine, mostly kilometers. But if we're talking about something like the size of our galaxy, or the distance to the next galaxy over, or the size of the universe as far as we can see, things like that, kilometers are too small. So we can use kilometers to talk about things within the scale of like our solar system, but not really anything beyond that. And that's the problem. Our solar system makes up almost nothing of what we know is out there in space. So we need new units to talk about those things that are bigger and farther away. And so that's where light years come in. Everybody's heard of light years, and we are going to calculate for ourselves how big a light year actually is. Notice that light years are a unit of distance, not a unit of time. I know it says year, but it's not a unit of time, it's a unit of distance. Because it's the distance that light travels in 1 year. All right, that's the thing that confuses a lot of people. But light years are a unit of length, or a unit of distance, if you will. For masses, the common units that we use to describe how much material is contained in an object, or for simplicity's sake, how heavy an object is we talk about, like, if you could multiply the Earth a bunch of times, how many Earths would you need to clone to have an equivalent amount of mass? So if you have something that's 3 times as heavy as the Earth, you could get an equivalent mass to that object by taking the Earth and cloning it a couple times so that you have 3 Earths. So we would say that such an object has a mass equivalent to 3 Earth masses. So an Earth mass is just the mass of the Earth. And we use that as a standard of measurement. It would be like if I wanted to measure the height of the Eiffel Tower in units of my own height. I could say it's this many mies tall. And you could each do that for yourselves, right? So just because we're from Earth, we'll use Earth masses. It's not like it's some magical standard of the universe or anything. It's just, this is what we have. Let's use it. I could say the Eiffel Tower is this many mies heavy, right? If I take my weight and the weight of the Eiffel Tower, I could say I would have to clone myself this many times to weigh as much as the Eiffel Tower collectively. Right, and so we do this with Earth masses, but we also do it with solar masses. And what that is that's the mass of the sun. So the sun is like 1,000,000 times heavier than Earth, give or take. And so if we find that Earth masses are too small for whatever we want to measure, then we'll use solar masses instead. And this is particularly useful if we're talking about how heavy a galaxy is, because a galaxy is made up of a ton of stars, plus some other stuff, gas and dust and whatnot. But if we say that a galaxy is made up of 100 billion stars, we could just assume, to get a rough calculation in our heads, we could just assume that if we're talking about a galaxy with 100 billion stars, that each of those stars weighs exactly the same as our sun. And then what we've got is, if we've got 100 billion stars and they all weigh the same as our sun, then that galaxy has a weight of about 100 billion solar masses. And we know what a solar mass is in kilograms. It was on the previous slide. We can then get a measurement for how heavy that galaxy is by just making this sort of like a rough calculation of, well, it's got about this many stars, and on average, let's say that those stars weigh as much as our sun, and we know how much our sun weighs, so we just do a little multiplication. 100 billion stars times the weight of our sun gives us the weight of that galaxy. And for timescales, seconds and minutes and hours are too short. Depending on what we're talking about, days are good. Days are good to talk about things, within the solar system, like how long it takes for the moon to orbit the Earth or Earth to orbit the sun. Years are also okay if we're talking about things like um, how long Jupiter takes to go around the sun. That's 12 years. Or if we're talking about how long Pluto takes to go around the sun, that's 248 years. Not enormous numbers, right? And if we really wanted to, we could start using millennia once we get out far enough. But what happens when you get to the age of Earth? Now, the Earth is, by our approximations, 4.5, 4.6-ish billion years old. So that's a long-ish number to write down, right? If we're just writing it down in years. So instead of inventing some brand new unit, basically all we do is instead of writing it in just years, you'll often see people write it down in units of millions of years or billions of years. Um, and so I've actually written A and A here because what happens is for a lot of times when you'll actually see this, it's talking about million years ago and billion years ago. So it'll say that like Earth formed 4.6 billion years ago. So the A is for ago. And I think later on in this lesson, I've written A again um, instead of like an R or just nothing. You could say billion years like this with YR for years, and the G it stands for giga, which is our prefix for a billion. If you have watched our video on the metric system for our math class. So anyway, this should probably be better off saying MYR and GYR, or just MY and GY. So some variations that you might see, but the point is that timescales are measured in millions of years and billions of years a lot of the time when we're talking about things on the scale of galaxies. If we're talking about things within galaxies, then maybe we can get by with years, but definitely outside galaxies, millions and billions of years are all that we can really use for timescales. So using these new units, I've only done the ones for mass and for time. Yeah, see here, this GYA should probably say GYR. So let's try and fix that. GYR. Okay, so we'll say GYR, giga years, right? That's billions of years. So while we're down here at the bottom of the page, we can just start there. The age of the universe is, well, it's this many years, which if you rewrite it in more normal numbers, you'll get that it's 13.8 billion years old. And so we can condense that down. Instead of having to write the word billion, we just write a capital G for billion, and then we write YR for years. Things like that. And for the mass of the Earth and mass of the Sun, well, that's easy because we've created this unit that is the mass of the Earth. So the mass of the Earth is one Earth mass, and this is the symbol for Earth mass. It's M with a little plus sign in a circle as a subscript. And then for the mass of the Sun, it's the same idea. It's one solar mass, and this is the symbol for a solar mass. It's an M with this subscript that's a circle with a dot in the center of it. That means solar mass. So if you ever see something in a news article and you see, blah blah blah, this object weighs 4 million solar masses, it's talking about 4 million of these, 4 million of these, 4 million of this many kilograms is the mass of whatever object that they're talking about. So that could be like a black hole, or maybe they're talking about some small galaxy that's got only a few million stars in it, things like that. So for the mass of Earth, mass of the Sun, we've just invented these two units. So the mass of the Sun is one solar mass, and the mass of Earth is just one Earth mass. So fairly straightforward. Now, for sizes and distances, because we're going to switch over to using light years, I want to show you guys how we actually get the size of a light year. So let's do that. Now, I know that this lesson has already gotten very long, but this is an important concept, so I totally get if this is something that you've already had to split across two classes. But basically then the first half was scientific notation and this intro, and now the second half is all about light years, basically. So, first things first, a common misconception is that light years are a measurement of time. And I know why people think that. It's, well, you see the word year in the name light year, right? And we think, well, years are a measurement of time. I don't know what light has to do with it, so a light year must be a measurement of time as well. This is not the case. A light year is how far light travels in 1 year. How far light travels, that's a unit of distance, right? So that's a very important point. If you're talking about distances in astronomy, light years are what you should be using, not light years as a unit of time. That's different. That's, well, we don't use light years as a unit of time. There are other things you can use as units of time, like giga years, for example. So now let's do a little bit of math, a little bit of calculation, and see if we can figure out how big a light year actually is in terms of our normal units. So I'm not going to make you do the calculation. I'm going to go through the calculation with you, and I might not take a super long time to do it just because I don't want this lesson to be like 2 hours long. But the first thing that we need is the speed of light, which is this number right here. And this is exactly what the speed of light is, no decimals necessary. And because this is what we call a constant of nature, we give it a special name, which is represented by a lowercase c. So on the next slide onwards, you're going to see up here in this top corner, I've written c equals like this number, or maybe I've written this version of it, but you'll see that in a little box in the top corner on the following slides. And I'm just telling you now that when you see that c, that means the speed of light. So this is the value of the speed of light, but we can see that this is, well, it's 299 million and then something something. That's pretty close to 300 million. So instead of working with this number that's difficult to multiply and do things with, let's round that off, because all we want is an approximate answer. Let's round that off to 300 million. So we don't have to worry about all these extra digits. We'll just round it off to 300 million. It's a little bit off what the actual number is, but it's good enough for what we're trying to do here. We're just trying to wrap our heads around how big a light year is. Now, one extra thing we could do to make this easier for ourselves is, instead of writing it in meters per second, we could write it in kilometers per second. Because a kilometer is a bigger unit of measurement, the number should get smaller. So because a kilometer is 1,000 times bigger than a meter, this number is going to be 1,000 times smaller than that number. So we just shaved off 3 zeros, and we've got a 3 and 5 zeros kilometers per second. So that's 300,000 kilometers per second. Cool? Cool. Now we can write that in scientific notation, right? Because we've got a 3 and then just a whole bunch of zeros after that. So we can condense that down. You don't have to do it for a number that's only 300,000, but this is just so that you can get a little bit of practice, get used to seeing a little bit of scientific notation. So we could write this as 3 times 10 to the 5 kilometers per second. Perfect. Now we've written down the speed of light in scientific notation and in units of kilometers per second. So that's the number that you're going to see up here in the corner on the following slide. Now, here's the thing. Light years measure the distance traveled by light in 1 year. But this speed right here, let's think about what this is telling us, and we can look at this one if that's easier. 300,000 kilometers per second. What does that mean? What do those words mean? Per second means for every 1 second, right? So if I've got 300,000 kilometers per second, that means that light is traveling 300,000 kilometers every single second, right? Let's explore this on the next slide. So if we've got that the speed of light is 300,000 kilometers per second, so keep in mind that this thing is exactly the same as 300,000. I've just written it this way to get you used to seeing these numbers and not panicking when you see these numbers. But this number right here is 300,000. So we know the speed of light is 300,000 kilometers per second. What that means is that each second light will travel this distance, right? This distance per second. Each second, that's what this part is telling us, is each second this distance will be covered. So that means that in 1 second, light travels 300,000 kilometers. Cool. In 2 seconds, well, that means it traveled 300,000 kilometers the first second, and then it'll travel another 300,000 kilometers in the second second. So it's traveled a total of 600,000 kilometers. And we can remember that 600,000 looks like this. And that's a 6 followed by 5 zeros. So I can write it as 6 times 10 to the 5. And that's what we've got here. 6 times 10 to the 5. 600,000 kilometers. That's how far light has traveled in 2 seconds, right? And in 10 seconds, it'll have traveled, well, instead of 3 times 10 to the 5, it'll have traveled 3 times 10 to the 6, right? Because when we multiply by 10, we just tack on a 0. You guys can explore that if it's not making perfect sense, but basically, in 1 second, it travels 300,000 kilometers. In 10 seconds, it travels 10 times that, so 3 million kilometers, which we can write in scientific notation like this. Now, you might say this is in scientific notation, but why did you write it that way instead? The proper way, if you're writing something down in scientific notation, is to have only one digit before like a decimal point. So right now what we've got is effectively it's a 30 and then a decimal point. So that's not proper. We've got 2 digits before that. So if I just move the decimal point over here, so instead of a 30, I have a 3, then I make up for my moving the decimal point to the left by 1 spot by increasing the exponent on the 10 by 1. So if that's not making sense, don't worry about it. The idea is just that, so we know that light travels 300,000 kilometers in 1 second, and it'll travel another 300,000 kilometers every single second, right? That's what it means for that speed to be that speed, is that each second it'll travel that distance. So if we use that pattern, we can figure out how far light travels in a year if we just figure out how many seconds there are in a year, right? Because each second light travels this distance. So if we just figure out how many of those seconds we can stuff into 1 year, then we'll have the distance that light travels in a year. And this is the formula that we actually use to calculate it. So the distance that light travels is the speed at which it travels, which is always that number, times the time that we're interested in. So the time that we're interested in is a year, but we don't know how to work with a year right now because the speed is given to us with seconds. So we need to just figure out how to write down 1 year in terms of seconds, and then we can just multiply that by the speed. The distance that light will travel in a year is going to be equal to the speed of light times the number of seconds in a year. That's what we need to do. Now we have the speed of light already, and we're interested in finding the distance. So all we need to do is write down the time in seconds. So I'm going to keep that equation here just so that that reminds us of what we're trying to do. Now let's figure out how many seconds are in a year. That's a little bit of a daunting task, so let's break it down into thinking about how many seconds are in a day. And then from there, we can take how many days are in a year and get the number of seconds in a year. That's our goal here. So we figure out the number of seconds in 1 day, which is an easier task. And then once we have the number of seconds in a day, well, we can just multiply that by how many days there are in a year to get the number of seconds in a year. So that's how that works. Once again, if you have any questions about this, please do let me know. I want to help make sure that you understand what's going on here. I'm not going to be testing you on the math and stuff, but it's really cool to see how we get the measurement of what a light year actually is. So I'm just trying to walk you through that, and I don't want you to be hopelessly lost. So if you're getting stuck, let me know, and I will see if I can help you out. But anyway, so our first step, how many seconds are in a day? Well, we can break that down further. We know how many seconds are in a minute, right? So we've got 60 seconds in a minute, no problem. But we don't want how many seconds are in a minute, we want how many seconds are in a day. So we can take it in steps. We know how many seconds are in a minute, cool. We know how many minutes are in an hour. Cool. So we get how many seconds fit into 1 hour, and that's 3,600 or 3,600 seconds in 1 hour. Cool. But again, we want how many seconds there are in a day. So we just have to look at, okay, we've got the number of seconds in an hour, and we know that there are 24 hours in a day. So the number of seconds will just be however many seconds you have per hour, each hour, right? Seconds per hour. So this is how many seconds we have in an hour, and this is how many hours we have in a day. Hours per each day, right? So we've got 3,600 seconds every hour, and then we've got 24 of those hours. So if you just multiply these two numbers, you get the number of seconds per day, the number of seconds that occur each day. And that's 86,400 seconds. Cool. Now we have a number for how many seconds there are in a day. So our next step is to figure out how many seconds there are in a year. And to do that, we will use how many days there are in a year and multiply it by the number of seconds in a day. So we've got 86,400 seconds in a day, and we know that there are 365 and a quarter days in a year, right? This accounts for leap days and such. So it's not exactly that, but it's close enough for what we're trying to do. So there are 86,400 seconds each day, and there are this many days in the year, 365 and a quarter. So the number of seconds in a year, well, that's just going to be how many seconds we have each day times the number of days we have each year, and that gives us the number of seconds in a year. And so that's just taking this 86,400 and multiplying it by that number there, 365.25, and this is the number that we get at the end of it, 31,557,600 seconds in 1 year. Cool? Cool. Now, let's think back. What were we actually trying to do? We're trying to figure out the distance light travels in a year. We have the speed of light in kilometers per second, and now we have the time in seconds, right? This is the number of seconds per year. We don't really need to worry about that per year part. This is the number of seconds in a year right there. So we can just throw in that number. Right? Think back to what we had before. If we can figure out how many seconds are in a year, we can figure out the distance that light travels in a year, because we know that each second it travels this far. So now that we have the total number of seconds, we can figure out how far the light has traveled, because each second it travels this far, and we know how many seconds there are in a year, so now we can figure out how far light travels in a year. And so if we go ahead and we do that calculation, we get, so this is the speed of light, roughly, in kilometers per second, and then this is how many seconds we have each year, right? That's what these units are telling us, seconds per year. This is how many of those we have. And so if we go through that calculation, we get that light will travel this distance each year, right? That's what I was saying about we don't need to worry about the per year part, because that was by design. We were talking about a specific 1 year period. But anyway, what we get here, this answer is telling us that light travels 9.5 times 10 to the 12 kilometers each year. That's what this is telling us. So that's the distance that's equal to 1 light year. And we can just write that out as a normal number. So 9, so I'm going to write the 9, and then I'm going to write the 5 without the decimal, right? Because I'm trying to write it out as a normal number. And I just need to make sure now that there are 12 digits after, well, after the 9. That's all I really care about, right? This decimal I'm getting rid of. All I need to make sure of is that there are 12 digits after that 9. And so the 5 is the first of those digits. And then after that, I just add zeros. So this is the second digit, the third, the fourth, the 5th, the 6th, the 7th, the 8th, the 9th, the 10th, the 11th, and the 12th kilometers. And so this would be, if we had a number in here, that would be the hundreds, this is the thousands, this is the millions, this is the billions. Wait, have I done? Yeah, okay, yeah. So this would be the This would be the thousands, this would be the millions, this would be the billions, and this would be the trillions. So we've got 9.5 trillion kilometers here. So 1 light year is equivalent to about 9.5 trillion kilometers. And if we want to round that off, we could round that off to 10 trillion, which we can write really easily this way as 10 to the 13, right? Because that would just be a 1 followed by 13 zeros. That's a 0. And there we go. So that's how many kilometers are in 1 light year. And well, now we can use that to rewrite those numbers that we saw before of the size of the galaxy and the distance to the nearest galaxy and so on. So let's see that. And so here we go. Using the calculation that we did just now to figure out the size of a light year, we can take this size of the Milky Way and rewrite it in terms of light years. And if you Google it, there's some discussion about whether it's more like 100,000 or more like 200,000, but we aren't really caring about that. What we care about is that it's roughly in the family of hundreds of thousands of light years. It's not tens of light years and it's not billions of light years. It's roughly 100,000, give or take another 100,000. So that's the size of the Milky Way expressed in light years, symbol Ly. And the distance to the nearest galaxy, once again, bonus points if you can tell me which galaxy that is. The distance to the nearest galaxy, the nearest big galaxy, I'm not counting our Milky Way's satellite galaxies, is 2.5 million light years, right? 10 to the 6. That means we've got 6 digits after the 2. That's telling us that that number 2 is in the millions place of that number. So 2.4 million light years away is where that galaxy is. And this is how we would write that distance out in kilometers. But we can see that in kilometers, that's an enormous number, right? We've got to have like a 20-digit number in total, the 2 and then 19 digits after it. Whereas if we write it in light years, the unit of measurement is bigger, but the whole number is now only 7 digits long, the 2 and then 6 more digits after it. So in that way, we can use new units of measurement to make sense of things in space. And so you'll see that light years are a very, very common unit of measurement when we're talking about things in space. And there are more units, but seeing as this lesson is already very long, which I kind of suspected while I was making this slide, I decided we're not going to worry about these additional units, especially since I don't intend to test you on the math. But anyway, I'll just tell you a little bit about them. So the first one is the astronomical unit, and that's basically the average distance from Earth to the Sun. So Earth is 1 astronomical unit away from the Sun. And this is about how far that is in kilometers. It's about 150 million kilometers or 93 million miles. Then we've got the parsec, and this is complicated to explain how we get the measurement of what 1 parsec actually is. If you guys are interested, I can explain that in a future video or in like a little supplementary video to this one. But suffice it to say for now that a parsec is equivalent to a little over 3 light years. So it's even bigger than the light year. So if you thought light years were big, parsecs are bigger. And it turns out parsecs are too small to talk about things that are very far away, or like if we're trying to talk about the size of the universe. So instead of using parsecs, we'll use gigaparsecs, which is 1 billion parsecs, or 10 to the 9 parsecs. So that's like 3 and a bit billion light years is 1 gigaparsec. So there are these additional units. There are others that we could talk about if you guys are interested. These are sort of the main ones that I didn't talk about. Anything besides that would be probably less useful to you than the ones that you're seeing here. But we're not going to worry about those because I'm not going to test you on those. I might just ask you, because I've told you now, I might just ask you, you know, what does an astronomical unit represent? What distance does it represent? and I might ask you, you know, what's a parsec equal to in light years, but I'm not going to ask you to do any calculations of tell me, you know, if it's this many kilometers, convert that into parsecs. I'm not going to ask you that. The most I'll ask you on a test or an assignment is to convert, or not even to convert, just to tell me what is 1 parsec in light years. That's it. I'm not going to ask you anything more complicated about these, so do not worry about those. And yes, for those of you wondering, parsec, that sounds familiar. Yes, it does appear in Star Wars, and yes, it is used incorrectly. It is used as a unit of time in parsecs in Star Wars. Keep in mind that because a parsec is a multiple of light years, and light years are a unit of distance, parsecs are also a unit of distance. So this is something that has been pointed out by many, many, many people on the internet. This usage of parsecs is wrong in Star Wars, but there you go. Now you know a little cool thing that you can go home and tell your parents about today is, hey, I learned that Star Wars made a big mistake. It's not a huge deal, but yeah. So now you guys have learned about some of the units that we see in astronomy. I promise not all our lessons are going to have this much math and numerical stuff going on, but I just wanted to explain what scientific notation is, why it's useful, particularly in astronomy. It's also useful in things like chemistry and physics and biology, I'm sure. But it comes up a lot in astronomy because we just happen to come across very, very large numbers, and we didn't build the units that we use to measure things with, you know, the universe in mind. We didn't come up with the kilogram with the Milky Way galaxy in mind, right? We came up with the kilogram to describe the weights and masses of things on a human scale, right? Um, but there you go. So I know there was a lot in this lesson, and I hope that you guys have split this across 2 classes because, good gracious, if you haven't, I would like to know how you managed to fit a 76-minute lesson into a 40-minute class. But yeah, if you have questions, please leave a comment down below, send me an email, fill out the Google form on the website that I created, and I will get back to you as soon as I can. I'm checking my email every night specifically for questions from you guys, and I will get notifications of comments that you guys leave on the videos, which I also check for every time I upload a new one. So, if you guys don't have any questions, which it's great if you don't, but don't be ashamed if you do, don't be embarrassed. Please ask me and I would love to clarify those for you. But yeah, I will see you guys in the next video. Have a good one.